Professor,
Yep.
do you know what the final is?
No, I don't. It's sometime middle of December. That's all I know, but I don't know the exact date.
We don't have any more exams coming up, right?
No, it looks like we may have to skip third exam because of time constraints. We are kind of behind. So to be able to finish everything, we have to skip the exam. The exam takes 3 days, preview and then exam day and then review after exam. So it's a long process. 3 classes are taken. So I may have to skip. I'm not sure. But if time permits, the third exam will be the day before the last day.
Okay, got you.
Class before the last day. The
All
last
right.
class, okay? I will confirm that sometime next week.
Okay, thank you.
Mhm. Also, apparently we will not meet this Wednesday because according to John Jay calendar, this Wednesday will be a Friday. So if you have a Friday class, that'll meet, but our class will not. So there's 1 more minute, so I'm still waiting for everybody to join.
Professor,
Yeah.
what was your morning class time again? 8 o'clock?
Yes, 8 o'clock. If anybody wants to attend the morning class instead of the afternoon, you'll have to let me know ahead of time so that I send you the invitation.
I want to do that, so I'll send you an email.
Yeah, send me an email requesting invitation for the morning class.
Okay, okay.
The 2 classes are always parallel, so you can always attend the other one instead. But then you had to let me know ahead of time.
Professor?
Yeah.
I logged in on time, but it was taking a long time to connect. Did you get my name in the attendance?
Yeah, I haven't taken attendance yet, just so you're okay.
Okay, thank you.
Mm-hmm. All right, it's 12:17 now, and I'm taking attendance. All right, try again. Okay, I'm sharing the screen now. We're going to proceed with the discussion of the conditional probability. So let me get the whiteboard. All right. Okay, so this is where we left off, exercise 6. We did problems like this before, but I just wanted to do one more problem on the conditional probability. So this problem gives you the count of each section on the Venn diagram. Now, remember, the problem may not tell you whether we have count or probability, but you can tell by looking at the numbers. So another student just came in. Okay, so the numbers are numbers will be decimal, fractional numbers if they are going to be probabilities. Okay, so in this problem, the left side of the E has 15 elements. The middle part has 5 and 20 in the F, which is outside of E. So 40 elements outside. So using these, I can count how many elements are in the sample space. All you have to do is add these numbers up. 40 inside the circles, 40 outside, so 80. Total number is 80 for the sample space. All right, so the first question is, what is the probability of E? It's not tricky, so go ahead and answer that. Probability of E, anybody? Somebody has to answer that. It's a straightforward question. It's not tricky question. Can anybody tell me the probability of E?
20.
20 is the number of elements in E. So remember I said all these numbers represent count of elements. So 20 elements are in E. So what is the probability of E?
Is it 1/4
What number divided by what number led to that?
divided by 80?
20 divided by 80, that's right. 20 over 80 are the numbers. 20, I'm trying to type that, 20 divided by 80. There are 20 elements in the event and 80 elements in the sample space, so 20 divided by 80. Probability of F, somebody?
25 divided by 80.
25 over 80. Okay, probability of E intersection F, anyone?
5 over 80.
5 over 80. E given F, okay, that means F has occurred, then the probability of E occurring. What are the numbers?
5 over 25.
5 over F has occurred, yeah, 5 over 25. 5 over 25. F given E.
5 over 20.
Right, 5 over 20. Are E and F mutually exclusive?
Yeah.
Remember the definition, two events are mutually exclusive if and only if they cannot occur at the same time.
Oh, so
So the answer is
no, they're not.
no,
No.
because they can occur at the same time. Whenever there are elements in common, they can occur at the same time. Because remember, the actual outcome is only one number. If that one number is in E, then E has occurred. If it is in F, then F has occurred. The question is, can E and F occur at the same time? Yes, because there are elements common to E and F. So if one of those is the actual outcome, then E and F occur at the same time. So therefore, these are not mutually exclusive. Going to the next picture, next exercise 7, the two circles are not meeting each other. So things are going to be slightly different. The count of sample space here is 65. 65 is the count of sample space. All right, what is probability of E? Anyone?
15 over 65.
15 over 65. Very good. And probability of F?
20 over 65.
Yes, 20 over 65. And E intersection F?
0.
0, right, because
They're mutually exclusive.
the E intersection F is empty, so the probability of E intersection F is 0. The count of elements is in E intersection F is 0, so the probability is 0. Okay, are the E and F mutually exclusive?
Yeah.
Yes, these two are mutually exclusive. There's nothing common to them. So yes is the answer there. Probability of E given, no, F given E. Probability of E occurring given F has occurred. So let me see if anybody can figure that out.
Isn't it
Doesn't happen.
0? Oh, sorry.
Go ahead. Go ahead. Sorry.
So the probability is?
Isn't it like 0 over 15? Because there's no chance that that would happen. E wouldn't happen if F is happening because they're mutually exclusive.
Right. Basically, probability of F given E means F, yeah, you can look at it two different ways. The intersection is empty, so if you apply the formula, the numerator is 0, right? Probability of E given F given E equal to probability of F intersection E over probability of E. F intersection E is empty, so probability of F intersection E is 0, so the whole thing is 0. That's one way to do it, applying formula. Another way is, look at the picture. If F has occurred, then your outcome is inside F, right? Your outcome is only one unit, one outcome. If F has occurred, then the outcome is inside F. If it is inside F, it cannot be inside E. There's nothing common to that. So therefore, E cannot occur if F has occurred. So therefore, probability of F occurring given E has occurred is 0. So two ways to do it. Apply formula. The formula is here. You learned it in the last class. Probability of E given F is probability of E intersection over F. Similarly, F given E, probability of F given E is probability of E intersection over probability of E. The second event, the conditional event, is always the one in the denominator. Apply that, then the numerator is intersection P, probability of E intersection F, and that's 0 in this case. So that's one way. Another way is to look at it directly. If E has occurred, then F cannot occur. Probability of E given F. What is that?
That's also 0.
0, right. So let's read the conclusion in the box here. If E and F are mutually exclusive, then if one of them has occurred, the other one cannot occur. The conditional probabilities are 0 if they are mutually exclusive. So mutually exclusive events have conditional probabilities 0. Okay, now we're going to do some application type problems with conditional probability. So first we need to understand what kind of situations are conditional probabilities. Here this problem asks you exactly that. Professor Skinner found that in his 2 sections of Math 120 class, 10% failed in section 1, 18% failed in section 2. State this as a conditional probabilities. That's our question. So I'm going to explain that for you. If I define, so let's say I'm taking a random student. That random student fails a class is one event. So event F is student fails. And the other event is the student is in section 1. That's the other event. I will call that E, in section 1. G would be student is in section 2. So you have to break up the individual events and name them. Then you can describe these probabilities as conditional probability. So 10% of the students in section 1 failed. That means if I take a student randomly, if the student if the student is known to be in section 1, in other words, given that the student is in section 1, what is the probability that he fails? That's what 10% is. 10% is the probability that the student fails, given that he is from section 1. So failing, given that he is from section 1, is 10%, same as 0.10. The other one is 18% of the students in section 2 failed, and that is as a conditional probability for failing, given that the student is in section 2. That's what 0.18 is. So all these, so when they give you that 2 pieces of information, student failed from section 1, so that's conditional probability. The student, 18% of the student section 2 failed, that's a conditional probability. And identifying them as conditional probability is important to do the application problems involving conditional probability. Exercise 8 is a similar one. Among the company's newly hired trainees, 24% are technical trainees. Okay, so 24% of all the trainees are technical. And 18% of all the trainees are clerical. Now it goes on to say 8% of the technical trainees are college graduates. Now that is conditional probability. 8% of the technical ones are college graduates. And the 4% is also conditional probability. But let's go down to the definition of the events. T is trainee is a technical one. C is trainee is a clerical one. G is trainee is a college graduate. All right, the first question is probability of T. In other words, if I randomly select a person from this these trainees, what is the probability that the trainee is technical trainee? That's what probability of T is. Okay, anybody? It's not a tricky question. It's fairly straightforward. 24% of all the trainees are technical trainees. What does that mean? Isn't that the probability? Remember, percentage number is also probability. So 24% of all the trainees are technical trainees means probability that the randomly selected person is a technical trainee is exactly that, 24%. So equal to 0.24. What is the probability that it is a clerical trainee? Randomly selected person is a clerical trainee.
0.18.
Yeah, 0.18, 18%. What is the probability that G given T? That means probability that it is college student, right? G means college graduate, not student graduate, college graduate, given that he's a technical trainee. So person is randomly selected, and that person has been found to be technical trainee. Then what is the probability that he or she is a college graduate? Anybody? That number is right here. 8% of the technical trainees are college graduates. That means within the college, within the technical trainees, 8% are college graduates. That means if the person is already known to be technical trainee, then the probability that he's a college graduate is what that 8% is. 8% of technical trainees are college graduates. So within the college graduates, 8% are technical trainees, means the probability for college graduate, given he's a technical trainee, is exactly that number, 0.08. Hold on a second, Elkin. Okay, so 0. Like I said, I'm only just checking your understanding of the words, translating the words into conditional probabilities. So 8% of the technical trainees are college graduates, means within the college graduates, 8% are technical trainees. That means if you already know the person is college graduate, then already know that the person is technical trainee, then 8% of them are college graduate, means there is conditional probability that it is college graduate, given that it's a technical trainee. So 0.08 is the answer there. Okay, probability of G given C. What is that number, anybody? 0.04, right. Okay, so now here we just introduced the idea of words translating to conditional probabilities, and application problems are coming up later where you will have to use these ideas. Exercise 9 is again a problem on Venn diagram. We have done problems like this before. So this is exercise for you to do. So I expect someone to give you the answers. Probability of E given F. You can apply formula or directly take the numbers from the picture. If you apply the formula, probability of E given F is, let me write on the board, probability of E given F equal to probability of E intersection F over probability of F. Okay, what are the numbers?
1/4? Oh, you mean the formula? 0.1
0.1 over
0.4.
0.4, which is equal to 1 over 4. Part B is E complement given F. Okay, anybody see the answer for that? Let me clear the board. And I'm going to copy this picture.
One minus what we had earlier.
I'm sorry, one more time.
I was saying like one minus what we had on A.
That's right. That's exactly right. Part A is probability of E complement given F. Second one is E complement given F. And those two are complementary. And we went over that in the last class, that they add up to 1. So therefore, probability of E complement given F is 1 minus 1 over 4, which is 3 over 4. Now, even if you don't recognize that, We can do it directly from the picture. So F has occurred, and what's the probability E complement will occur? That's our question. So let me go to the board. I'm going to show you. If F has occurred, then you are limited to F. So EF. So now you're in here, in F. Your outcome is only one outcome. F has occurred means your outcome is in this event, right? Inside this circle. So if this has happened, how can we have E complement occurring? E complement occurring means outside of E occurring. So if the outcome is already inside here, how can it be outside of E? Only if it is here, right? Only if it is here, then it can be, it's outside of E. So what's the number for that? 0.3. 0.3 over entire F. F has occurred. So that's our sample space. So probability of F goes in the denominator, which is 0.4. So 0.3 over 0.4 is 3 over 4. So you can always do it directly or apply the properties you learned. Okay, going to probability of E given F complement. So let me put another picture up. So let me see if you can figure out. If you have, then let me know.
I put 1 because I said that it's 0.4 over 0.4.
So your answer is 1, you're saying? Okay. F complement has occurred. I see where you're going wrong. Yeah. F complement has occurred means we are outside of F. The actual outcome is outside of F. That means we are somewhere here, right?
Oh wait, yeah, I have to include the 0.2.
Right.
Right.
Exactly.
Okay. Yeah. So it'd be 0.4 over 0.6.
0.4 over 0.6 is correct. Very good. So we are outside of F. So now the only way E can occur is if the actual outcome is in here. So therefore, the number for this part is 0.4. So 0.4 over 0.4 plus 0.2. 0.4 plus 0.2 is the outside of F. So 0.6. That's equal to 2 over 3. Okay, very good. So now this, we learned this before. Probability of E given F and probability of E complement given F have to add up to 1. And I'm going to algebraically prove that. Probability of E given F and E bar given F. E bar given F. I showed you in the last class using a example I illustrated, but now I'm going to algebraically prove it. E given F, probability of E given F equal to probability of E intersection F over probability of F, applying the formula, plus probability E bar given F means E bar intersection F divided by probability of F. Since the denominators are matching, that'll become the common denominator, and the numerators add up, E intersection F plus probability of E bar intersection F. So E given F and E bar given F, E intersection F and E bar intersection F will be, let me show you on the picture, E and F. E intersection F would be this part. E bar intersection F would be all of this outside of E in F. The union of those two is exactly F. So therefore, these two probabilities, probability of E intersection F and E bar intersection F, add up to probability of F. And so they cancel out to 1. So algebraically, I proved that E given F and E bar given F have probabilities adding up to 1. It is useful sometimes to know that in application problems. So let's do this exercise 10. Professor Walker's class is taken only by juniors and sophomores. He knows probability for a junior to get A in his class is 0.2. So identify this as a conditional probability and identify the complementary conditional probability. Okay, so let's, I'll go over that. Let me clear the board. Okay, so if I define the event, it's always the experiment is taking a random student. So if I take a random student, that student is student is a junior or sophomore. Those are some of the events. So I'll call J, the student is junior. Randomly taken student is junior. And S to mean he is sophomore. And the other event is the student gets A. So event A is getting A grade. All right, then this event that they have given 0.2. So let's identify that. That's the probability that a junior will get A. That's same as saying probability to get A given that the student is junior. That's what that is. That's 0.2. So the question now is, what is the probability that a junior doesn't get A? That's same as probability of A complement given J. And what would that be? We just learned that probability of any event given anything conditional event and the complementary conditional event have probabilities adding up to 1, right?
Oh, so 0.8.
0.8. Another way of saying it is, within the juniors, 20% get A, so 80% don't get A. As simple as that. But describing it as conditional probability helps you do problems involving conditional probability, which are coming up later. Going to example exercise 11, a jar contains 5 red marbles, 3 green and 4 white. Jack takes 1 marble. E is marble is red. Event F is marble is green. G is marble is white. Then write the following events as conditional events and find the probabilities. Okay, so exercise 11, part A, we have to first identify these events as conditional events and then find the probability. What is the probability that it is red given that it is not white? So tell me the notation first. P of what, comma what? What given what?
P of E given G complement.
Yes, E given G complement, exactly, very good. So now let's find the numbers. So given that it's not white, what is the probability that it is red? Anybody has an answer? We already know it's not white.
5/8.
5/8. 5/8 is correct. If anybody needs explanation, ask for it. Second
Yeah,
question.
could you please explain?
Okay. If it is already given to be not white, that means the 4 white marbles are out. We are now limited to the 5 red and 3 green marbles. So that 8 is the total number, and among them 5 are red. So 5/8. Okay.
Yeah, thank you.
Mhm. Okay, the next one. What is the probability that it is green marble given that it is not red? So let's identify them as conditional probability first. So give me the symbols. Probability of what given what?
F given E complement.
Right, F given E complement. Okay, so can somebody give me the numbers now? It is not red. That's given. So probability for green.
Three out of seven.
3/7, right. Okay, very good. So let's go to exercise 12. This is a slightly different problem. And so I need to go over that. A red die and a blue die are rolled. What is the the colors are because there are two different dies. So getting a 5 on the first and getting a 5 on the second are two different things. That's why they have two different colors. What is the probability that the sum of the resulting numbers is 7, given that one of them is 5? That's so it's easier to do it directly. Two dice are rolled. So given that one of them is 5, what is the probability of getting 7? So if it is given that one of them is 5, then the event that has occurred, I'll call it F, is one of them is 5 means it can be 5-1, 5-2, 5-3, 5-4, 5-5, 5-6, 1-5, 2-5, 3-5, 4-5. We don't want to repeat the 5-5. So next one is 6-5. So there are 11 elements. Count of F is 11. And the event E intersection F, or given that F has happened, what is the, how do we get the numbers adding up to 7? That will be E intersection F. Given that this event has happened, what is the, what elements will make the total 7 to happen? Only the 5-2 and 2-5, right? Only these two can make a 7. Given that your element has to be in F, F has already happened. So within F, only 5-2 and 2-5 add up to 7. So therefore, the probability, the conditional probability that E occurs given F is 2/11. So F has occurred means your outcome is one of these in F. And among them, only 2 elements make the other event E happen. So therefore, probability of E given F is 2/11. Okay, now whenever they take marbles, if they take them without replacement, then you're going to have conditional probability situation. So this problem illustrates that. Exercise 13 illustrates. A jar consists of 4 red marbles and 3 green marbles. 2 marbles are taken one at a time without replacement. That means you take one marble and without putting it back, you take another. So now, if I define E as first marble is red and F is second marble is red, then these events, then let's think about the probabilities. The probability of E we can find. That's the first event. So you're taking a marble and what is the probability that it is red? Okay, that's a straightforward question. Can anybody tell me the numbers? There are 4 red marbles and 3 green marbles. I'm taking 1 marble. What is the probability it's red? That's basically the question. Somebody has to answer it. It's an elementary question.
Isn't it 4/7?
4/7. Yes, that's it. Okay, let me write that. 4/7. So that part is easy. For the first marble, it's easy. Now, can we find probability of F? The second marble is red. So can I simply find probability of F? No. Why? Because the second, if the first event has happened, then there are 1 fewer red marbles.
So it's 3/7.
Oh, that's if the first event has happened. So is there a probability for F that we can find? That's my question.
Would it be 3/6? Because the first thing already happened, so
Oh,
you're
yeah.
1 marble out.
That's only if first event has happened, right? Without saying anything about first event. If I simply say, find the probability of F, can we find that? No, because it depends on whether E has occurred or not.
So what would be the answer?
So there's no answer. Can we find probability of F? The answer is no. Okay, there's no such
Oh,
thing.
I see.
I'm sorry?
I see what you mean now when I'm reading C.
Okay, all right. So part C says, what is the probability of F given that E has occurred? That we can answer. We need to know whether E has occurred or not to be able to find F, right? Because it affects. So this is when the events are dependent. We call them dependent events. So if E has already occurred, that means 1 red marble is already taken. So for the F, so going to F, if E has occurred, then there are only 3 red marbles now. So what is the probability given E has occurred?
3/6.
3/6, right. 3/6 is correct. Very good. Now, what is the probability of F given E has not occurred? That means the first
Wouldn't
one,
it be 4/7?
I mean, yeah.
4/7
because E hasn't occurred.
E hasn't occurred, but we did take 1 marble out, right?
So it'd be the same thing.
No, not 3/6.
3/7. I'm like confused because you said if the first thing happened, then it would be 1 marble less.
No, if E has occurred, then the first marble was red. We did take 1 marble. If that marble is red, then the probability of F occurring is 3/6. That's what part C is.
Mm-hmm.
If that event has not occurred, that means the marble taken was not red. That's what it means. The marble was taken. Okay, it was not red. So there are how many red marbles left?
Professor, I have a question.
Yeah.
So you're saying for D, a marble was taken, but it was not red?
Right. E.
So a green one was taken.
Yeah, it must have been green. That's what it means. So
How did you get that from this sentence? I'm sorry.
the E has not occurred means we are taking 1 marble. The first marble was taken. And event E represents first marble being red. If E has not occurred means first marble was not red. That's what it means.
Oh, so it's 4/6.
Yes, 4/6. First marble
So
was
2/3. You wouldn't simplify it. You would say 4/6 or
You
2/3.
do simplify, yes, but that's not the point. The numbers you know how to reduce, but I'm asking about the numbers. There are 4 red marbles out of 6 marbles. 1 was taken, and that's not red. Means 4 red marbles are there out of 6 marbles. Okay, is that clear to everybody now? E has not
Mhm.
occurred means the first marble was not red. So that means all 4 red marbles are still there. But a marble has been taken, so its total is 6. So 4/6. If anybody has questions, you have to ask me now. Moving on. So that finishes this entire worksheet. So we're moving to the next one. That will be continuation of this, but some more ideas and principles are going to come in. And this is the last worksheet on probability. When this finishes, we are going to start statistics. Someone asked about the test. It's unclear whether we can have one or not, but if we finish statistics now, we are not doing a whole lot, very little we are doing statistics. So we may still have time. If you have time for the test, it'll be the class before the last class. That's going to be the test.
But
Professor,
we have a final right after.
The final is not right after. We'll have the last class will be the review. You know, I will answer questions on the practice final. And then I think final exam is the following week or something like that.
Professor,
Exactly. I'm sorry for interrupting you. But
Professor.
Yeah.
I have to leave because I have an appointment.
Oh, I'm sorry. Yeah, we went over.
Is it okay if I?
No, we're not. Oh, yeah.
I have an appointment.
Who is this?
Kalia.
Kalia, okay.
Yeah, I have to leave 30 minutes early.
All right, but it'll be a lateness in your record though.
How was that a lateness? I was here the whole time.
No, the class is not finished.
I know it's not finished, but I have an appointment to attend.
Yeah, so you shouldn't have made the appointment during class time. Okay.
What?
You shouldn't have made a doctor's appointment during class time.
Well, I can't change that.
All right, you can discuss that later, but leaving early is same as lateness. All right.
Hey, whatever, bye.
All right. We are continuing to multiplication rule for probability. So basically, we are going to rearrange our formula. So let me clear the screen. The formula that we learned for conditional probability, I'm writing on the board. Probability of E given F is probability of E intersection F over probability of F. Okay, so if I multiply both sides by probability of F to get rid of the denominator, then I have these two canceling out. So probability of E intersection F equal to, I'm writing this on the left side, equal to probability of E given F times probability of F. So basically that same formula rearranged gives you a way of computing probability of E given F, E intersection F, that is probability of E and F happening, is equal to probability of E given F occurring times probability of F. Similarly, I have the other formula, probability of F given E equal to numerator is intersection of both, so that's same as the other numerator, E intersection F, divided by probability of this event, E. So again, if I multiply by probability of E on both sides to get rid of the denominator, then I have probability of E intersection F equal to probability of F given E times probability of E. So two versions of formula for intersection. Probability of E intersection F can be E given F times F or F given E times E. Always this latter one is multiplied. So two versions of formulas. Both of them are called multiplication principle for probability. There was a multiplication principle for counting techniques that we discussed at the beginning of counting techniques. That's called counting technique, multiplication principle for counting. This is called multiplication principle for probability. So you have to remember the names. This is going to be useful in word problems involving conditional probability. So we're going to do some examples, but before doing that, let's understand the tree diagram. The tree diagram is a way of showing the conditional probabilities and probabilities in any experiment. So whatever the experiment is, if you write a line, draw a line to show one possible event. So if this is E, then another event happening, given this has happened, will be branching out of this one. This event, this line represents another event happening given E has occurred. So after E occurring, this event occurs. F occurs given E. That's what this line represents. So if E is not the only possible event, if there's another one, then another branch will go here. And then if you have another branch going out of that, that'll represent F happening given EG has happened. That's what that represents. Okay, so now the E and G, if you only have two branches, E and G, that means they are complementary. They have to add up to 1. The probabilities have to add up to 1. So when you're drawing tree diagram, you have to account for all the possible things. So if there's another possible event that can happen as the first event, then you have to have another branch to show that. The probabilities of all these events will have to add up to 1. You have to account for all the possibilities when you're drawing the tree diagram. Now we're going to do more tree diagram in a few minutes. Another point in the tree diagram is this is E and this is F given E, and see probability of F given E times probability of E will give you probability of E intersection F. So if you multiply this probability on this line and the probability on this line, that'll go here. That'll be the probability of E intersection F. Probability of both happening equal to probability of this happening times the second one happening. So that's what the multiplication principle is. On a tree diagram, we put all those probabilities. We're going to do that in an example, so it'll be more clear after that. So let's do the problem example 13.1. So let me clear the screen. Example 13.1 says, 2 cards are drawn without replacement from a 52 card deck. What is the probability that the first card is ace and the second card is king? Now, notice that this word is and here, not given. So this is not conditional probability they are asking for. But they are dependent events. Whether the second card is king or not depends on whether the first card was ace or not. If the first card was not ace, then it could be a king. So that will affect the second one. So it does, it is a dependent one. So therefore, we need to apply the conditional probability formula. So let's introduce some names. The first card is ace is one event. So I'm going to call it A to mean ace, the first letter of ace. First card is ace. Okay, so that's my A. And this king, K will be second card is king. Then the question is the probability for both to happen. So we need probability of A intersection K, both happening. So we need to write that in terms of one of these formulas, these back on the worksheet. Probability of E given intersection F is either probability of E given F times probability of F or probability of F given E times probability of E. So which one is applicable here? That's what we need to figure out first. Okay, so which probability can I find? A given K or K given A? Well, look back at the problem. The first card is ace, is the first event, is first card. Second one is second king. So the second card is king, given first card is ace, is the one we can find, because the first one is the, it's going to happen first. So K given A is what we can find. A given K is not appropriate here, right? So probability of K given A is the one we can find. So therefore, times probability of the second one, A. That's the formula that's applicable here. So what is the probability of A? Probability of A means we took a card and that's ace. What's the probability that's ace? Anybody? This probability of A, what's the number? That's our first event. We are taking the first card, and what is the probability that is ace? How many ace cards are there? How many aces are there?
4.
4,
Out of
52.
52. There are 4 aces out of, we are taking one card randomly. It could be any one of the 52 cards. So the sample space has 52, and the event of ace has 4 cards. So 4 over 52. Now, the other number is K given A. If A has already occurred, what is the probability of K occurring? In other words, if the first card was ace, then what is the probability second card is king?
Would that again be 4 over 51?
4 over 51, exactly. The first card was ace, and that means all 4 kings are still there. So 4 out of 51. There are only 51 cards left. There was the first card taken, and that was ace. So there are 51 cards left. So therefore, 4 times 4, 16 over 51 times 52, whatever that number is, you have to reduce it. But this problem can be done using permutation combination as well. So recall that this problem also reads as, there are 52 cards and we are taking 2 cards. And what is the probability that one is ace, one is king? So we did that when we learned counting technique. So 13.2 says, do this as a counting technique problem. Okay. Then the event of taking 2 cards has how many elements? The sample space has how many elements? We're taking 2 cards from 52. So that's combination 52 comma 2, right? Number of ways of taking 2 cards. That's equal to 52 factorial over 52 minus 2 factorial, which is 50 factorial. So that's equal to 52 times 51. That's the count of sample space. The event is one card is ace and the other card is king. Okay, the one card to be, the first card taken to be ace, and how many ways are there to get ace as the first card? There are 4 aces and you're choosing, so the first card, one card that we chose to be ace, how many different ways are there? Combination 4 comma 1. There are 4 aces and this has to be one of them. Times number of ways of getting the second card, king. That's also combination 4. There are 4 kings. We're choosing one of them. C41 is 4. C41 is 4. So 4 times 4, 16. So the probability of E is 16 over this number, 52 times 51. And that's the same number we found here. So this can be done both ways. The two, because the one card is ace, the other one is king. If you're both going to be ace and different aces, I mean, if they're going to be both ace or anything like that, if there's intersection between them, then you cannot do it as a counting technique. You have to do it as a conditional probability problem.
I have a question.
Yeah.
Are you doing, for the sample space, is it a combination of permutation? Because I don't think, wouldn't it be 52 over 50 and then another 2 on the bottom?
Yeah, C52, comma 2. Is that what you're asking about?
Yeah, if you're doing combination, right?
Yeah, combination, because we are taking 2 cards from 52 cards.
Okay.
Okay. So a number of ways of doing that is C52 too. So not all of these problems can be done by counting technique. So, the condition, if there's an intersection between them, then it's not permutation combination problem. It has to be, it can only be done as conditional probability problem. So let's go to another one. This is exercise. It's supposed to be for you to do, but I will get started and then I'll expect you to answer the questions. So let's clear the screen, and 2 cards are drawn from a deck of cards. What is the probability that the first card is diamond and the second card is red? Now the problem here is diamond is also red. So, so you have to be careful with the numbers. Now we can do this directly. But directly or by using formula. I mean, both ways will work. Now we want both of them to happen. So let me define my events. We're doing exercise 1. If I define my events, first card is diamond. I'll call it D. First is diamond. And red, R will be second is red. Then the question here is probability for D intersection R. That's what they're asking for. So that can be found by D given R times R or R given D times D. So which one applies? Which conditional probability should I write here? The first one, diamond, is the first event. Second one is red, is the second event. So we can only find the second event given first event happened, right? So red given diamond is what we can find. Second card is red, given first card is diamond. We cannot find the other way around. So therefore, this times probability of D is the formula that applies. Okay, so let's find the probability for D, this one, probability of D. That'll be just probability of getting diamond. You're selecting one card, what is the probability it's diamond?
1 out of 13.
No, we're taking a card from the 52 card deck. And what is the probability that card is diamond?
13 out of 52.
Right. So 13 over 52. The sample space has 52 elements because the card can be any one of the 52 cards. Among those cards, 13 are diamond. So the probability for getting diamond is 13 over 52. Now this one is probability for red, given that first card was diamond. We have taken one card already, and that was diamond. What is the probability that it is? The second card is red. That's what we are looking to find out. Anybody? Now remember, diamond is red. What are the red cards? Diamond and hearts. The total number of red cards in a deck is 26, diamonds and hearts. So what is this probability? Given that the first card was diamond, what is the probability that second card is red? Nobody can see that? Altogether, there are 26 red cards. The first card taken was a diamond. So that's one red card gone. So what is the probability that the second is red?
So there's
Twenty.
only 25 red left.
Say again?
So there's only 25 red left. Is that what you?
25 red left. So 25 over
51.
51, yes. One card has been taken, so only 51 cards altogether left. Out of those 51, 25 are red. Right? Understand?
Yeah, that makes sense.
Okay. So the product of these is your answer for both happening. Part B, first card is hot and second card is black. So I have to define them. H is first is hot, and black B for second is black. Okay, then the probability we are looking to find is H intersection B, both happening. So should I write B given H or H given B?
B given H.
B given H. We can only talk about second thing happening given first has happened. We cannot talk the other way around. So B given H times probability of H. Okay, what is the probability of H?
13 out of 52.
13 over 52, right. There are 13 hearts out of 52. What is the probability that is black given hearts has already occurred? Now, heart, the black cards are heart and spade. So there are 26 black cards in a deck. So what is this?
Same thing as the last question.
Yes.
25 over 51.
25 over 51, same as the last, right, very good. All right, now if I am supposed to draw the the tree diagram for this event of taking a card from a deck of cards, then the tree diagram has to be complete. So that means from this one node, you have to branch out to all possible outcomes for the first card. The first card can be diamond, heart, or club, or spade. And probability for diamond is 13 over 52. Probability for heart is 13 over 52. Club is also 13 over 52. 13 over 52. You can see that they add up to 1. They have to add up to 1. If they don't, that means you missed something. These are the only possibilities for the first card to be, and I covered all possibilities, and these probabilities add up to 1. Now, given D has occurred, the second card to be red or black was the question. So red and black are two branches. And if it is not red, it's going to be black. So these are complementary events. So those two will also add up to 1. So this branch is actually red given D. Red given D has occurred. That's same as this, red given D, 25 over 51. And this represents black given D. So if the first part was diamond, then that was red. So that means there are 26 blacks now out of 51. So you can see that 25 over 51 and 26 over 51 add up to 1. They have to add up to 1. So similarly, here also there are two, red and black, red and black. And if you put those probabilities, then the tree is complete. At the end of the tree here, the number we write will be the product of D and R given D. This is R given D. That product will be the product of both happening, same as this intersection. This product goes at the end. So if I'm writing a number here, that'll be 25 over 51 multiplied by 13 over 52. Similarly, other branches. So if they ask you to complete the tree for the experiment given, then you had to write all these probabilities on the tree. Okay, so let's do this exercise on trees. This problem says the tree diagram is already given to you. You need to figure out the remaining probabilities and also the probabilities that they are asking for. Okay, so remaining probability means probability of A has to be found. Can somebody tell me what probability of A should be?
Point 1.
0.1 is right, because 0.5 plus 0.4 is 0.9, and since all three should add up to 1, A must have 0.1. Okay, going to the other branch, what is the probability of this E here? That E represents E given A. So what is the probability there? Nobody can see that? Somebody has to answer that, otherwise I'm not convinced you understand me. What is the probability of E? Since there are only 2 branches here, they have to add up to 1. Remember I explained? You have to write all the branches, and if you miss one, then the tree is wrong. So this is a complete tree, means the E has to be complementary to D. So the probability for E should be 0.7.
Oh, okay, that makes sense. Okay.
All right. And similarly, this E represents E given B has occurred. Okay. And what is that?
0.6.
0.6. This E represents E given C has occurred.
0.3.
0.3. Okay, now let's answer these questions. Probability of E given A.
That was 0.7, right?
That's 0.7. That's right. That's exactly what number we wrote here. I didn't write anything here, but because I couldn't, but that we found that to be 0.7, right? Even though we write E there, that's actually E given A. E happening after A occurred. That's what that line represents. So that's 0.7, so that's the answer. Okay, E given C is?
Would that be 0.3?
E given C is 0.3, right? And A intersection E. A intersection E, both A and E happening. Nobody can see that? This is event A happening, has probability 0.1. this, we write E here, but it's really, this probability represents E given A. And probability of E given A multiplied by probability of A is what probability of E intersection A is. So always this, at the tip here, we write the probability of intersection, which is actually probability, this probability multiplied by this probability, E given A times A. So 0.7 times 0.1, that's what that is, 0.07. Also the next branch, B, and then I have, now let's go to the question. The question is about C intersection E. D, E. And this is 0.7, so this is 0.3. So how do I find the number for here? This, that's the probability of C intersection E.
Are you multiplying 0.4 and 0.3?
Right, multiply 0.4 and 0.3, 0.12. So part D answer is 0.12. Okay, so let's do the exercise 2. This is similar to what we did before, but let's do it anyway. Probability of E intersection, F intersection E needs to be found, and that's given by F given E times probability of E according to our formula. So the problem says, find them individually and verify that this rule is true. Okay, so let's find each one. First one is probability of F given E. Probability of F given E. Okay, what are the numbers for that? Given E has occurred, the probability for F occurring will be
5/20.
5/20. And probability of E is the sample space has 80 elements. So what is probability of E?
20/80.
20/80. And let's directly find probability of F intersection E. Directly find it. What is it?
5/80.
5/80. So the problem says verify the rule. In other words, if I multiply these two, do I get 5/80? That's our question. F given E times probability of E is 5/20 multiplied by 20/80. Okay, 20 and 20 cancel out. It gives you 5/80, which is same as this. So it verifies that the rule is true.
Professor, could you just clarify that F given E, just real quick, how you got the 5/20?
F intersection E.
Yeah.
Is that you're asking, or F given E? Which one?
F given E.
F given E, the first one.
Yeah, I just want to make sure I understand it.
Okay. F given E means E has occurred means your sample space has 20 elements. See 20 there, right? E has occurred,
Okay.
right. And then now after E has occurred, which element F has to occur means only if you are one of the 5 elements here, then F will occur, right?
Oh, yeah. Okay, thank you.
Right, okay. So exercise 3 says, jar contains 5 red and 6 green marbles. One ball is taken without replacing, and then another ball is taken. So 2 are taken one after the other. What is the probability that first is red and second is green? So if I define R as first is red and G as second is green, then R intersection G is what we need to find. right? Both have to happen. So I need to write which conditional probability, R given G or G given R?
A given R.
G given R times probability of R. Okay, the probability of R is 5 over 11. That's just 5 out of 11. And probability of G given R is, it means first ball was red. So what is the probability second one will be green? That will be, all 6 greens are there. So 6 over 10, right? One ball is gone, so 10. The product will be the probability of both happening. All right, so we'll stop here. And your homework is already up, and the due date is right now set for Wednesday, but I need to change it to Monday because this Wednesday we don't have class. According to John Jay calendar, this Wednesday will be a Friday. So if anybody has classes meeting Friday, then that class will meet, but our class will not meet on Wednesday. So I will change the due date to Monday for this assignment. So I will see you Monday, and everybody have a great Thanksgiving.
Professor, can you stay after class?
Yeah, I will. If you have questions, you can hang around. Otherwise, you can leave. So everybody have a nice Thanksgiving and nice weekend. I will see you Monday. Anybody has question, hang on.
Thanks, Professor.
Mhm.
Yeah, I have a question.
Okay.
Do you think it will be possible for you to post this video today? Because I think like I probably missed something and I want to rewatch it.
Okay. Yeah, yes, I always post it as soon as I can.
Okay.
This system takes a while to convert it to the appropriate format, and that's why the delay is. Okay.
Okay. All right.
So
Thank
I will post it today. Yes, I promise that.
you. Have a good Thanksgiving.
You too. Bye-bye.
All right.
Professor, I'm just gonna wait for everybody else to like leave, and then I'll talk to you separately.
All right. Anybody else who had a question, feel free to go ahead.
Hi, Professor. I didn't have a question, but at some point I got kicked out for like a minute or two, but I joined immediately. I just wanted to let you know that I didn't come late.
This is Nicole Nito, right? Yes, you joined around 1:12. What happened?
You kind of froze and I couldn't hear you, and then it said that I got disconnected from the internet or something. We have someone working here, so
Your sound
it
is
was just
pretty
someone
bad. I'm not able to understand. Are you saying that you were in class from the beginning, but at some point you were kicked out?
Yes.
Yes. Okay. All right, then I will mark you in. If you were here from the beginning, then you are in my attendance record. I took attendance at the beginning, so you must be in that record. So you should be okay. All right.
All right. Have a good Thanksgiving.
Bye-bye. Okay, anybody else other than Tatiana having question? I have Tanzina, Anissa, Lena Elkin. Do you have question? All right, maybe they're gone then. Okay.
Yeah, so I just wanted to let you know that I just joined a few minutes late, but I dropped my mom off at the hospital, and that's why I was late. But I tried to come like directly on time.
Okay, but that's not an excusable.
No, it's fine. I just wanted to let you know because I had told you in the email that my mom was having like just finished her radiation, and she was having another procedure done for her breast cancer. So yeah, I just had to drop her off. I just wanted to let you know, just in case like you forgot or something. It's fine. I know it's not excusable. It was only like 2 minutes, but I just wanted to like let you know.
Okay, if it is 2 minutes, maybe it's okay.
All right.
Yeah, so yeah, I see I have written down that You were 3 minutes late. So that would be still marked as on time. Okay.
Okay, I appreciate it. Thank you so
Okay.
much. And I'll be sure to, if I have any questions about the homework or anything, I'll let you know. But if I'll go back and watch the video for like the first 5 minutes of class, so that way I don't miss anything.
Yeah, that'll be great.
Thank you so much, Professor.
You're welcome. Have a nice Thanksgiving.
You too. Happy Thanksgiving.
Bye-bye.
Professor?
Yep.
So, I've caught up a little bit today, but I'm still a little bit behind in like understanding probability.
Okay.
I was wondering if I know that getting credit that I'm not going to get credit for it, but I was wondering if the last 2 homeworks, if they could be opened up so that I can work on them, because I didn't really do much on them. I wasn't really understanding it then, but I think that I can work on it now and sort of catch myself back up.
Okay. Basically, you're asking me to extend it, and
I mean, I completely understand if I don't get credit for it. I just want to work on it so that I can, understand it going forward.
yeah, that's a reasonable request. Actually, if you missed if you missed a few problems on those assignments, then you don't have the full understanding of probability.
Yeah, no, I actually like missed a lot of them. For one of them, it was like almost all of it. I was actually working with a tutor for this. Sorry, I'm looking at the homework so I can tell you exactly which ones I'm talking about.
Okay.
I was actually working with a tutor for homework 20, and we had a really hard time getting through stuff. And then for homework 19 and 18, homework 19, I didn't even do anything. So
that would be bad. If you continue without doing any assignment, you're going to be lost and you can't understand anything anymore.
yeah, I know. That's why I'm also trying to participate more.
All right. So what do you need? 19 and 20?
18 and 19.
Okay.
Oh, as well as 17. I had already done some for 17, but I didn't really finish it. I got 18 out of 26.
Okay. All right. What I'm going to do is I'll write down your grades for them. I cannot give you an unfair advantage.
Yeah, that's understandable.
Yeah, so I'll write down the grades and then I'll open it up, extend the due dates. There's no other way to do this. I'll extend the due date so it'll allow you to do them, and basically it'll allow you to get credit for them. But then I had to change the credit back to what you got before.
Yeah, that's completely understandable.
All right, okay.
Also, is office hours only 2 Mondays and Wednesdays, or?
Yeah, only on Mondays and Wednesdays.
You're not doing office hours this Wednesday though, are you?
Yeah, this Wednesday, there'll be no office hours because we are not supposed to be having anything.
Okay.
But if anybody requests an additional meeting, I can set that up.
Oh, okay. That's awesome.
All right. So if you're running into questions, you want a meeting with me, feel free to ask for it. But if you ask for it in an email message, then check your email message periodically, because I will be setting up a meeting and sending you a link.
Okay, that sounds good.
All right.
Thank you. Have a good one.
You're welcome. Have a good one. Anybody else with any question there? All right.